In this video, I will review the topics that are prerequisite to calculus and that I would collectively refer to as algebra. And the main objective of this review is to make sure that you understand the place of algebra in the landscape of lower division math courses, and you can identify the main subject or subjects of interest and the tasks learned in what I would call an algebra course. So let's get started with reviewing the map of lower division math courses. And here you can see that a sequence pre-calculus, calculus 1, and calculus 2 form a pipeline from the beginning of mathematics into um, a variety of courses that we would call lower division math courses. And algebra sits right here, right before pre-calculus. It's one of the branches, the other one being geometry, trigonometry. And algebra has an important role in the um, in this uh, path to calculus. So let's talk about algebra. The word algebra itself loosely translates from Arabic into finding the unknown. So if anyone speaks Arabic and wants to um, confirm that, please let me know in the comments. Or on the other hand, if that's a complete BS, also let me know in the comments. Um, the main object, or rather subject of interest in algebra is going to be an equation. So I'm kind of giving you heads up over here. It's not a secret. And the main task, and actually, let me correct myself, it's not just equations, it's also inequalities, and it is also systems of equations and inequalities. And the main task that we will be performing here is to solve and to graph. And one of the large points that I'm going to make very soon is that to graph and to solve are equivalent tasks. Meaning, if you know how to solve, you should know how to graph, and if you know how to graph, you know how to solve. However, if you ask ChatGPT, it will tell you that it's not the same, which is weird. So, uh, let's start with the conversation about what is an equation. And an equation, on one hand, it can be viewed just from the visual appearance, just as an object of interest, as we take an expression and we set it equal to some other expression. And if you, instead of equal sign, put inequality sign, then it's going to be inequality. So here's an example. You have 1 plus 2x equals 3 plus x. So we have an expression on the left-hand side. We refer to it as the left-hand side. And we have an expression on the right-hand side. And altogether, this is what we would call an equation. On the other hand, so this is one point of view. On the other hand, alternatively, we can refer to an equation as a conditional statement. And conditional, what does conditional refer to? Well, to answer that, we have to understand what exactly is a mathematical statement. Mathematical statement is anything that can be considered as true or false. For example, 1 plus 2 equals 3 is a true statement. Alternatively, 1 plus 1 equals 3 is a false statement. We can similarly define like inequalities, but uh, later we'll find out that there is a close relation between equations and inequalities, so let's just continue focusing on equations. So 1 plus 2 equals 3 being true statement, 1 plus 1 equals 3 being false statement, means that if I introduce a variable like this, if I say 1 plus x equals 3, then in this case, I don't know if this statement is true or false. So we will say it's a conditional statement. And what is the condition here? The condition is the value of x. So this statement is true when x equals 2. And this statement is false for x equals 1 and many other values. So in the context of this particular example, we would refer to x equals 2 as a solution. And x equals 1 will be an example of something that is not a solution. Now, equations may have one solution, as the one that I just showed you. So x plus 1, or rather, what was it, 1 plus x? 1 plus x equals 3 has one solution. Equations may have more than one solution, such as this one. This equation has two solutions. So the solution here is x equals 2. The solution here is x equals 1 and x equals -1. The equations don't have to have solutions. So this is an example of an equation that has no solutions. Is that it? Are these the only options? No, there are infinitely many options. So for example, this equation has infinitely many solutions. So the idea is that you may not necessarily know how many solutions are there, and to know the number of solutions is not necessarily the same as knowing what the solutions are. So what I'm writing here on the right side is actually called the solution sets. So the definition of a solution set is the set that contains all solutions. So we can write it, we can express the solution set for the first one as using the set builder notation or just the set notation. This is already written in a set notation. And when there are no solutions, we're using the empty set notation. And this brings us finally to the definition, what does it mean to solve? So to solve an equation, means to find the solution set. In other words, it means to find all the solutions of the equation. That's what it means to solve. So the main question now is how to solve. So this is kind of the main um, question associated with the main task in algebra. And the answer, as always, the best answer is always depends. So how you solve an equation in algebra depends on two things. One is the number of variables, and the two possible answers are one or two variables. Yes, there are equations that have three and more variables, but you're probably not going to be able to solve them by hand, or this is not something that you learned in a standard algebra course. So it depends on the number of variables, one or two, and it also depends on the type of the equation. So let's talk about when you have one variable first. If you have an equation in one variable, such as this one, or this one, or this one, or this one, if you look at the solution sets of these equations, they have one thing in common. All of those solution sets live on the number line, meaning that they can be visualized as a point or a collection of points on the number line. So, for example, here is the solution to the first equation. This is the solution to the second equation. A blank number line is the solution set to the third equation, which is an empty set. And everything but one, so I'm going to make a hole here and shade everything but one, is the solution set to the last equation. So the first observation is that solutions of equations in one variable can be visualized on a number line. Now, that doesn't mean you know how to solve it yet, right? So to solve, as I said before, depends on the type of the equation and what types of equations are there. If you watched the previous review that I've made of pre-algebra and arithmetic, then you know the answer to this question already. The type of the equation is determined by the operations that are used, and consecutively, it also determined by the type of expressions used on both sides of the equation. So normally to classify an equation, we write it in a form, we have 0 on the right-hand side, and then you look at the left-hand side, and if you're just looking at the left-hand side and you're not looking at the equal sign, this is just an expression. So the type of the equation is determined by the type of the expression. And the types of expressions that we know are linear, quadratic, polynomial, rational. There are altogether 8 of them, just like the number of operations that we learned in arithmetic. Rational, what was the other one? Exponential, radical, logarithmic, and absolute value. So these are the 8 different types of equations. Now, is it possible to have an equation that has the features of several types? Yes, but again, you didn't learn too many of those in algebra. So I don't expect you to solve an equation that has components like exponential components and logarithmic components, but I do expect you to know how to solve standard equations covered in standard algebra course, which are listed on this slide. Now, let me briefly go over the solving methods for each of these types. Again, the purpose here is not to teach you, but to just remind you of those methods. And if you want me to get into more details for any of them, just let me know in the comments, and I'll be more than happy to provide more details and examples. But here you go. If you have a linear equation, then we solve it by isolating the variable and by writing it as x equals a. How do we isolate the variable? We use the properties of equations. What are those properties? Let me uh, find an empty slide, and I'll list here properties of equations and inequalities. And the idea is that everything that we learn in math has properties. Numbers have properties, equations have properties, operations have properties, and it is worth knowing all such properties. So the properties of equations are the following. If you have A equals B, then you can add or subtract a number to both sides of the equation. If you have A equals B, then you can multiply or divide both sides of the equation by a non-zero number. You can multiply by 0, but that will severely affect your solution set. So you don't want to do that. So all of these operations do not change the solution set. They only change the appearance of the equation. For positive numbers, you can take the square root of both sides. So if both sides are positive, then you can take the square root. If both sides are positive, you can take a log of any base. If both sides are positive, you can raise both sides to an odd power. And the question is, why can't we add it to an even power? What's going to happen? The solution set will be affected by that. What's the difference between odd and raising to the odd power and even power? To answer that question, we actually have to kind of advance through pre-calculus and learn functions. So the answer will be you can apply a one-to-one function. We don't know what one-to-one function. We can pretend for a second that we know what one-to-one function is. So just remember this. When you have an equation, you can apply a one-to-one function to both sides of that equation, and that will not affect the solution set. So that's what all of these rules have in common. So instead of writing all of this, we can just write it's okay to apply one-to-one function. So what's wrong with squaring both sides? Well, as you know, squaring is not one-to-one function, so squaring is not okay. Now, just like equations have properties, inequalities also have properties. If A is less than B, I'm trying to be fancy here. If A is less than B, then you can add and subtract a number to both sides of the inequality. You can multiply both sides by the same number, or divide by the same number, and inequality will not change if that number is positive, and it will change if the number is negative. Now, you can do other things with both sides of the inequality, and some interesting things will happen. So, for example, if you take the reciprocal of both sides, what's going to happen? I guess before we take reciprocal, let's raise it to the odd power. What do you think is going to happen if I raise it to an odd power? Um, the inequality will be the same. What do you think is going to happen if I apply the reciprocal? Well, the correct answer is that inequality will be flipped. What's the pattern here? The pattern is that if you apply an increasing function to both sides, inequality will not change. If you apply the decreasing function to both sides, then inequality will flip. So, as you know, reciprocal is a decreasing function, so inequality will flip. So these are the properties of equations and inequalities. So when we say here, isolate the variable to write the equation in this form, we mean isolate it by adding, subtracting, multiplying, dividing both sides of the equation by something to make it look this way. All right, absolute value equations solved using the property of absolute values. Quadratic equations can be solved in more than one way, depending on how it is given to you. You can either use factoring, you can complete the square, or you can use the quadratic formula. Radical equations are solved by isolating the radical first, and then using the definition of a radical. And power equations are solved in the same way. You isolate the power term of the equation and then use the definition of the nth root. Polynomial equations are solved by using the zero product property after factoring out the polynomial. And rational equations can be solved in two different ways. One by clearing the fractions, and then once you clear the fractions, you're going to end up with some other type of the equation that you should already know how to solve. Or alternatively, you can turn it into a proportion and then use the property of proportion. Exponential equations are solved by isolating the exponential term and then using the logarithm on both sides. And logarithmic equations are solved similarly by isolating the logarithmic component and then exponentiating both sides of the equation. Now, remember I said that the equations and inequalities are connected, and here's an example of how they are connected. So, for example, if you have to solve this inequality, then first you have to solve this equation. So we already know the solution of this equation. So we solve this equation and we get this answer. So the answer is plus or minus 1. Now, the solution of the inequality also lives on the number line. So to find the solution of this inequality, we look at the solution of this equation, and this equation divides the number line into 3 intervals. And these intervals entirely either belong to the solution set of this inequality or entirely are excluded from the solution set. How do you know if it's included or excluded? You can pick a test point and test your inequality. So if the test point is not a solution, then the whole interval is not a solution. So you can test it at 0, you can test it at 2, you can test it at -2, and you'll see that inequality is true here, false here, and is true here. So what does that mean? That means this is a solution of the inequality. This is also a solution of the inequality. Now, what about the boundary points? Well, the boundary points are analyzed separately, and it depends mainly on the domain of this inequality and whether the inequality is strict or not strict. So in this case, it's not strict, so I would have to exclude these points from the solution. So the final answer to this inequality will be from -infinity to -1, and from 1 to infinity. Now, the same is true in general for most of the inequalities in one variable. So if you understand the relation between the solution set of the inequality and its corresponding equation, then you're pretty much all set, and you would know how to solve any inequality in one variable, given that you know how to solve the corresponding equation. Now let's move on and let's talk about what to do with equations in two variables. Here's an example of an equation in two variables, x plus y equals 2. Now, to solve still means to find the solution set. When you have two variables, your solution set has to be made of solutions, and each solution has to present two values because a solution is a value or values that turn the equation into a true statement. So here's an example of a solution. So x equals 1, y equals 1 is a solution. X equals 1, y equals 0 is not a solution. But is this the only solution? The answer is no. So, and again, we're not surprised. We've seen other equations, even in one variable, when you have multiple solutions. So when I start writing these solutions, you're not surprised. And on the other hand, when do we stop? So we should acknowledge relatively fast that there are actually infinitely many solutions. So how am I supposed to write out infinitely many solutions? The answer is the graph. So since we have two variables here, I'm going to draw one axis for x, one axis for y, and now each solution corresponds to a point in this coordinate plane. So this is your 1, 1. This is your 2, 0. This is your 0, 2. This is your -1, 3. Is that it? No. If you continue figuring out the solutions, each one of them will correspond to a point. If you keep plotting these points, and if you keep doing it until you get tired, what are you going to see? Well, all these dots will form a line. So this line is the solution set of this equation. Why? Because again, it's made of points. Each point corresponds to an ordered pair, and each ordered pair represents a solution. So these are your solutions. So for equations in two variables, to solve means to graph. And it's actually true even for one variable, right? So in general, it does make sense to think of to solve and to graph as two equivalent tasks. Now, here's another rule of thumb. The number of variables determines the number of axes that you use. So equations in one variable need one axis, therefore you only need a number line. Equations in two variables use two number lines, and there you go. There is your Cartesian plane. Equations in three variables will require three number lines, 3 axes, and that's your three-dimensional coordinate system. Now, what I've said earlier about inequalities, the solution sets of inequalities being related to solution sets of equations remains to be a true statement, also in for equations and inequalities into variables. So here's an example. If I ever have to solve this inequality, I would graph the solution of the corresponding equation. So let me put this on the right side. I would consider the corresponding equation. I would produce the graph. So again, I would solve it. And the solution will be this line. And then do you see how this line divides the plane into two regions? Here's one region, and here's another region. Now, just like before, each of these regions either entirely a part of the solution set of this inequality or entirely excluded from it. So how do I know which side of this region is a part and which is not? I'm going to use some test points. I can pick a test point 0, 0, or I can pick a test point, let's say 2, 2. And I will test. You can see that at 0, 0, it's true, and at 2, 2, it is false. That means this part of the Cartesian plane is the solution set of this inequality. Now, it it doesn't take much effort to actually understand this idea. Once you get it, how it works for one variable, it works exactly the same way for two variables. So, how do we solve or how do we graph equations into variables depends on the type of the equation. So next I'm going to give you a list of solving or graphing methods for each of the different types of equations into variables. So to solve a linear equation, or rather to graph a linear equation, we isolate the variable y and then they use the slope-intercept form. To solve a vertical parabola, to graph a vertical parabola or to solve this quadratic equation, we can rewrite it in one of the three different forms, vertex, standard, or factored, and then use these steps to produce the graph. Similarly, we can graph horizontal parabolas. You can also solve this quadratic equation, solution of which is a circle, by following these steps. You also learned how to graph ellipses and hyperbolas, but those are just different shapes of a solution set for quadratic equations that look like this. Now, there are many other equations into variables that you probably haven't had a formal introduction to, but this is what they look like. So with a little bit of effort, you should understand how to graph all of these equations. And once you know how to graph something like this, we can refer to this, and this as parent graphs. And then we can use the idea of linear transformation and conclude that when you add, subtract, multiply, and divide, or add negative sign to the front of the input or the output, those have different effects on the graph. So adding a positive number to x will shift the whole graph to the left. So if you know how to graph y equals absolute value of x, then you would also know how to graph absolute value of x plus 5. You would also know how to graph absolute value of x over 3. You would also know how to graph y plus 2 equals x, absolute value of x minus 1, for example. So this is again the summary of what we refer to as linear transformations. Now, we cannot talk about algebra and not mention the fundamental theorem of algebra. So the fundamental theorem of algebra pretty much says that every polynomial equation of degree n has exactly n complex roots. Now, as you know, there is also the fundamental theorem of arithmetic, and there is also the fundamental theorem of calculus. Is there any connection between the fundamental theorem of algebra and the fundamental theorem of arithmetic? Well, let me remind you what the fundamental theorem of arithmetic states. It states that every number can be factored into a product of prime numbers if it's not prime. So it says that, for example, 42 can be written as 2 times 3 times 7. Now, the fundamental theorem of algebra, at first glance, uh, it doesn't say anything about factoring. But if you recall, the way we solve polynomial equations is by factoring. So when we say every polynomial equation of degree n has exactly n complex roots, it's the same as to say that every polynomial equation can be factored into a product of n, where n is the degree of the polynomial, many linear factors where each of these values is a complex number. Now, if you don't want to step into the complex number field, like a minefield, then you can simplify the statement of the fundamental theorem of algebra and say that any polynomial can be factored into a product of linear terms and quadratic terms, irreducible quadratic terms. So hopefully I'm not making it too complicated, but what I wanted to demonstrate here is that there is a connection between the fundamental theorem of arithmetic that is about factoring and the fundamental theorem of algebra, which may not sound like it is about factoring, but it is also about factoring. So these are the nuances that I would like you to know and remember about fundamental theorem of arithmetic and algebra. Now, to end this review, I want to once again remind you uh, what we discussed. We know that we are dealing with equations. Equations could be of one or two variables. When it comes to equations in one variable, we prefer to say we solve them. When it comes to equations of two variables, we prefer to say we graph them. But conceptually, it is the same thing. Now, how we solve, how we graph, depends on the types of the equations. And the types of the equations, I'm going to list them here real quick, are, once again, the same as the types of expressions from the pre-algebra. Here, if you haven't seen it yet, I would send you back to the pre-algebra review that I made earlier. So there are linear, quadratic, polynomial, rational, exponential, radical, logarithmic, and absolute value. Um, equations, just like there are linear, quadratic, polynomial, rational, exponential, radical, logarithmic, and absolute value expressions in pre-algebra. And the reason I keep bringing this up is that the types, the way we classify these objects is the same for expressions in pre-algebra. So in pre-algebra, we're talking about expressions. In algebra, we're talking about equations. But the goal here is to eventually move on to calculus or pre-calculus. And in pre-calculus calculus, this is going to be the same classification that we would apply to functions. So the sooner you learn it, the sooner you become familiar with these words, the better. Now, I would like to end this review with the list of some of the vocabulary that you have to be familiar with. This is the terms from algebra in one variable, and these are the terms from algebra in two variables. You should know all these terms, and not only know, you should be able to use them fluently when discussing whatever that is you are doing, whether you're solving an equation or simplifying or evaluating an expression or graphing an equation into variables. Again, that's it. The purpose of this review wasn't to teach you all of this, but to refresh your memory. If you have any questions about any topic or anything else I mentioned in this review, and you would like me to go into more details, please let me know in the comment section, and I will be more than happy to do that. Otherwise, that's it for now. Let me know if you have any questions.